So I thought since we couldn't do it in person, I was going to create a few lectures where I go through the solutions to the problems on the AIME II. I'm not going to guarantee that these are the best solutions. They're just the ones that I thought of when I saw the problems. So for example, the very first question, we're just trying to find the number of ordered pairs of positive integer solutions to this particular equation, 20m plus 12n equals 2012. So the first thing is everything's divisible by 4, right? So 20 divided by 4 is 5, 12 divided by 4 is 3, 2012 divided by 4, I had to think about it, but it's 503. And so now I want to find the positive integers that solve that equation. And right off the bat, it's pretty clear that if n is 1 and, m could be 100, right? And n could be 1, and that's a solution, right? Because 500 plus 3. And the trick is the only solutions you're going to have, because 5 and 3 are relatively prime, if m gets smaller by 3, n has to get bigger by 5. And then 5m will go down by 15, 3n will go up by 15, and it'll still be equal. That's the only way to make this work. And so the next solution, if m gets smaller by 3, you'll get 97. And if n gets bigger by 5, you'll get 6, right? So 97 times 5 plus 6. It's going to work. One gets smaller by 15, the other gets bigger. Well, if I get smaller by 3 again, I'm not going to keep doing this. I'm just trying to explain the reasoning. 94, and this one goes to 11. And so one keeps going down by 3, the other keeps going up by 5. They both have to be positive integers. When does it stop? Well, 100 is one more than a multiple of 3. So the last one we're going to get is when m equals 1, rather. And n, I guess, how many times did I have to go down by 3? I had to go down, I think, 33 times, right? I got 99 smaller than my original number of 100. And so, not that it matters, n had to get bigger by 5 33 times as well. I guess that's 165. So that one would be 166. I don't even need to know that. All I need to know is that the total number of times n got smaller 33 times. So including the first one, there were a total of 34 values for the positive integers. That is, n 1, then go up by 3 to 4, then go up by 3 to 7, all the way up to 100. There's 34 of those. And so the answer to the original question is 0, 3, 4. The next problem, you've got two geometric sequences. They have the same common ratio. The first term of the first sequence is 27, and the first term of the second sequence is 99. I guess I don't have to read the whole thing. You can pause this and read it yourself. But the point is that the 15th term of the first sequence, which remember will be a sub 1 times the common ratio to the 14th power, has to equal the 11th term of the second sequence. And again, it's also a geometric sequence, so the 11th term will be the first term times the common ratio to the 10th power. So just by dividing both sides by r to the 10th power, you get that r to the 4th power has to be the first term of the b sequence divided by the first term of the a sequence, which is 99/27, which I guess I could simplify because they're both divisible by 9. That's 11/3. Now, so the common ratio is the 4th root of 11/3. I don't care. I don't care. They didn't ask me for that. They asked me for a sub 9, which is going to be a sub 1 times r to the 8th power. So it's going to be 27 times, well, if r to the 4th is 11/3, r to the 8th is 11/3 squared. So that's 121/9 times 27. 27 divided by 9 is 3 times 121. Right? When you square it 11, you get 121, and everything else cancels, and we're left with 363, which is the answer to the second problem. For this third problem, and you should read it, pause the screen and read it if you haven't yet, we're trying to count how many ways you can pick 6 professors. You've got departments with 4 people in each department, 2 men and 2 women, and you're going to pick 2 people from each department. There's 3 departments, so you get 6 people in all, and you want to find only the ones that have 3 men and 3 women. So I found it useful to first think just about one department. So there's 4 people in a department. So I would say, okay, if I'm going to pick 2 people from that department, there's one way to pick them both to be the men. There's one way to pick them both to be the women. And if I'm going to pick 1 man and 1 woman, I could do it 4 different ways. Because I have 2 choices for who the man is and 2 choices for the woman is. They're independent. Great. So now I'm going to do this for all 3 departments. And I have to say, how am I going to get exactly 3 men and 3 women? Well, there's only 2 ways it can happen. One way is if I pick 1 man and 1 woman from each department. That's certainly possible. Well, there's 4 ways to do it from the first department times 4 ways to do it from the second department because they're independent times 4 ways to do it from the third department. That's pretty clear. There's 64 ways. But I could also have one of the departments I pick 2 men, another department I pick 2 women, and only one department I pick 1 man and 1 woman from each. So I have to think about all the different ways those departments could be. Was it the first department that has the 2 men, or the second, or is it the third? And which department has the 2 women, and which one has the 1 man and 1 woman? And then once I do that, I multiply that by how many ways, once I know which departments have which combinations of genders, how many ways there are to actually do it. So how does that work out? So there's 3 factorials to decide which department is which, because you've got 3 choices for who's the one that picks 2 men. Once you pick that, there's 2 choices left for who's going to be the 2 women, and then there's only 1 choice left for the department that picks 1 of each. And then once you know which department is which, there's only 1 way for the department to pick 2 men, there's only 1 way for the other department to pick 2 women, and there's 4 ways for that last department to pick 1 man and 1 woman. So it's going to be 3 factorial times 1 times 1 times 4, which is another word for 24. And since there's 64 ways to do it by method A, and there's 24 more by method B, that's a total of 88. So the answer to the question was 088. So here's my picture for question 4. You should read question 4. And frankly, I think they didn't write it quite as accurately as they might have. A lot of people were confused by it. I do think there is a single best interpretation, but they should have been a little more explicit about one point. Be that as it may, let's take a look at the problem anyway. So you've got Anna riding going west from that corner at 8.6 meters per second. Bob is going south at 6.2 meters per second, and Cal is going southwest, I guess, at 5 meters per second. And they're all going to meet up at point D. And I guess it's implicit in the problem, this is what they didn't say exactly, that Anna is riding along the perimeter. So when she reaches the west corner, she turns south, and then when she reaches the south corner, she turns east again. So she's going to go along the perimeter, as is Bob. They're all going to meet at point D at the same moment, and then we have to figure out the ratio of P to Q to R. I've labeled my diagram P, Q, and R. The only thing we know is that P is greater than Q in addition. So now let's just think about this. I'm going to, by the way, have to move my tablet up so that it's covering the problem. So be sure you've read the problem and know it, so I can actually get a little more space to do my writing. So what we know is that Anna travels, if you just add up the distances she goes on the rectangle, she travels 2p plus q minus r. Well, p plus q plus another p minus r. So 2p plus q minus r at 8.6 meters per second. Bob travels q plus r, and Cal travels the square root of q squared plus r squared. And they're each going at their own respective speeds. Now that I've done that, I don't even need the picture anymore, although the fact that q, r, and square root of q squared plus r squared is a right triangle might be suspicious to us all. Maybe it's going to be a nice Pythagorean triple that we're familiar with. But let's see if we can just write the ratios. So I'm going to go to another page. So this is it expressing it as times, right? The distance divided by the speed gives you the time it took to go that distance. And all 3 of these are equal. So now I've got these ratios, and I have to solve. Now they told me I'm not going to be able to solve for P, Q, and R explicitly. I'm just going to get their ratios. And when I look at these and I say, well, which one is going to be the easiest one to find a ratio for? I'm immediately struck by the last 2. Because there's no p's in them. It's just q plus r over 6.2 equals the square root of q squared plus r squared over 5. And in fact, when I look at those 2 equations, I'm struck by the fact that I can actually divide both sides of just the last 2. Q plus r over 6.2 equals root q squared plus r squared over 5. If I divide both sides by r, I can write everything in terms of q over r, right? Because the left-hand side, it's q over r plus 1 in the numerator. The right-hand side, I'm dividing by r, but that's like if I bring it inside the square root, I'm dividing by r squared. And so I wind up with q over r quantity squared plus 1. Take the square root of that over 5. That, if I write it in terms of x, that looks very quadratic equationist. I just have to square both sides and solve. I can probably simplify a little. So I try to put it all in terms of integers. So I multiply by 6.2, I multiply top and bottom by 5, so it's 31/25. Square both sides, and I don't have a calculator, so I'm just hoping things are going to simplify. I'm trying not to do any nasty arithmetic before I have to. And okay, so I'm going to multiply both sides by 25 squared, and I'm going to get it into a quadratic polynomial, and we'll see what we have. If you recognize the Pythagorean triples, you're better than I am. So, but I think it's going to work out nicely. Well, hope springs eternal. I mean, that's what I have right now. I just multiplied everything out. This is just algebra. But that's at least the difference of 2 squares. Oh, that's not so bad, because 31 squared minus 25 squared is 31 minus 25 times 31 plus 25. So I get that. 6 times 56 squared, 2 times 25 squared. Oh, there's an x missing. Yuck, yuck, yuck. But I can let's divide both. Let's divide the whole thing by 2 at least. Bleh. Okay, I'm not happy, and I'm sure cleverer people than me have already solved this in some other different way. But this is going to work. I see my way to the end of this because I know the quadratic formula. And oh, thank goodness, at least that thing inside the square root, as awful as it is the difference of squares. So I have high hopes it's going to simplify. Plugging into the difference of squares, it's 25 squared minus, oh, I should just do it. 6 times 56 is 336. I know that. And 25 squared is 625. So I get this, and I've been putting it off and putting it off. I got to do the arithmetic. Oops, I had a little mistake there. I said 636, but I meant 336, right? That's what it was. I was multiplying by 6, and I meant to, and I got the 6 in my hundreds place because of the 625. Anyway, there it is. It's correct. It's 625. Go back and look. 625 minus 336 times 625 plus 336. And what's nice is those I think are going to work out pretty well. In fact, they're 289 and 961. And oh, lo and behold, those are perfect squares. Do you recognize 961 as a perfect square? It was very helpful on this test. And I don't like multiplying 17 by 31 either, but it's not so bad. 17 times 3 is 51, and 17 times 1 is 17, so it's 510 plus 17, it's 527. Yes, yes, yes. So now at least I know what x can be. And just doing a little factoring, 1152 is divisible by a lot of powers of 2. In fact, I didn't even go all the way. Once I got it down to 32 times 36, I felt like I can finish it from here. And similarly, 98 is 2 times 7 times 7. And I remember 336, remember it was 6 times 56, so there's a 7 in there as well. So a lot of things simplify somewhat. And in fact, I get 2 solutions, either 24/7 or 7/24. That actually doesn't surprise me now that I think about it, because the original problem was symmetric in Q and R. Q plus R over 6.2 equals square root of Q squared plus R squared over 5. That was what I was solving. And so I don't know which one is Q and which one is R. Whatever solutions you get with Q and R, you could switch Q and R with each other and get another solution. So whatever ratio you get for X as Q over R, there has to be another solution where X is the reciprocal of that. So the 2 solutions are in fact reciprocals of each other. But now we haven't used the full problem yet, so let's go back and see which of these makes sense in the original problem. We have to use the other equation. Well, if Q over R is really 24/7, so Q is 24 times something. I don't know. I mean, the units don't really matter, but 24z and R is 7z for some z. Then what does that tell me? Remember, I also have the other equation. By the way, if you know your Pythagorean triples, that means that the hypotenuse is 25z. 7, 24, 25 is a Pythagorean triple. And since we have these equations, this relationship here, these were the ratios that we got. If we plug in Q and R and even square root of Q squared plus R squared, in terms of z, and I'm finding it easier to plug in using the square root of Q squared plus R squared because I knew the Pythagorean triple, so it's 25z over 5. You could use Q plus R over 6.2, 31z over 6.2. But now look what we get here for P. This is no good, because when you solve for P just by plugging in, you get that P is 13z, but that's less than 24z, and so the side P is less than Q. This solution doesn't work. So we just, I mean, the other solution is very similar. We just have to switch the Q and the R so that the ratio of Q to R is 7 to 24, not 24 to 7. So what changes here? Very little changes, except when I go through the work here, 2p plus q minus r, the q plus r over 6.2, or the square root of q squared plus r squared over 5, that's still 25z over 5. But the 2p plus q minus r is no longer plus 17z, it's now minus 17z. And now if we solve that for p, we get that 2p equals 60z. So p winds up being 30z, which is bigger than 7z. So the ratio of p to q to r is 30 to 7 to 24. 30 to 7 to 24. And so and those are 30 and 7 are in lowest terms. Even though 30 and 24 aren't, that doesn't matter. But so the sum is 30 plus 7 plus 24, which is 061 as the answer. So that's the first 4. Maybe I'll do some more of these. This is all I have time for right now, though.